Okay, as we mentioned in the last video, force is a vector, right? So it's very important that we break it up into components and that we're looking in each dimension when we are doing a force problem, okay? So whereas in the last problem, we could get away with just summation of forces equals ma, because it was just in one dimension, okay? If there's a problem that has two dimensions, right, we need to make sure that the components of the forces in x, right, the sum of all the forces in the x direction must equal m times a in the x direction. And the summation of forces in the y direction must equal m times the acceleration in the y direction, okay? This is the x and the y component of the acceleration, all right? Okay, so as is usually the case, before we actually do a problem, this is very abstract, and you might be kind of fuzzy, like, well, what does this mean exactly? Well, I'm going to show you, okay? So if you guys could go to the slide that says getting up on your tippy toes, okay? And in this problem, we have, it's like a calf, right? And then there's like a foot there, okay? And there's like, I don't know, toes in the foot, okay. Anyways, we have these two calf muscles, right? And they apply symmetric 200 Newton forces at these angles, okay? So like there's a force here of 200 Newtons, right? And then there's a force here of 200 Newtons, and they're symmetrical, which means it's the same angle, and it looks like it's 20 degrees for both. 20 degrees for both. Okay? All right. So now, here's the thing. As you can see, these two angles, these two vectors, these force vectors, part of this force vector is being applied in the y direction, and part of this force vector is being applied in the x direction. That matters. Okay? And so we remember that well, maybe you don't remember, but I'll remind you now so that you know forever and ever and ever. The component of a component of any vector that touches the angle always gets the cosine. Sometimes that's x. A lot of times we've been measuring the angle from the x axis, so that makes sense that the x component would get cosine. But that's not always the case, not when you measure the angle from the y-axis, right? So in this case, these y components, so there's going to be an fy there, there's going to be an fy there. That's going to get the cosine because it's actually touching the 20 degrees, right? Whereas this fx component here and this fx component here, that's not touching the 20, right? That's touching 90 minus 20 right here, which is 70 degrees, okay? So be aware of that. So in this case, our fx components are actually going to be 200 sine of 20, okay? So I got fx in this direction, right? So we'll call this fx1, we'll call this fx2, 1, 2, right? So this is going to be 200 sine of 20, right? So far, so good? That's this component right here. We have the magnitude of this vector is 200, and the degree is 20, and it gets the sign because it's not touching the 20. Okay, minus, this is moving in the negative x direction, so minus 200 sine of 20, okay, equals, and we're just going to put m equals ax there, okay? All right. By the way, this is a good point in the problem to stop and see what exactly are we looking for here. And it says, what is the mass of a human if the calf muscles apply symmetric 200 Newton forces at the angle shown? Okay. Assume as a person is moving upwards, assume the person is moving upwards at a constant velocity. Okay. So in that case, what do you know about acceleration? Well, it's going to be 0, right? So this equation gives you nothing special, right? This equation just says that 200 sine 20 minus 200 sine of 20, that's just 0 equals max, right? In other words, ax equals 0. We already knew that, okay? Sometimes, you know, one analysis in one dimension isn't going to give you anything too special, right? But it's much, much more interesting here to look at what's happening in y, okay? Now, one thing that I did not add to this vector yet is that this calf muscle, right, this human being has a certain weight, right? And that weight is being applied on this, well, to the entire body. But let's suppose that, you know, your leg, your ankle down there is taking the brunt of it, so this is going to be the weight of the entire body, right? Well, W equals mg. All right, so in this case, we have Fy2, right, going up, plus Fy1 going up, minus mg equals MAY. Okay? So again, all I've done here is read everything off of this free body diagram. I added up the two y components that are going up, right? Because that's positive, that's the positive direction. And I subtracted the one y component going down because we know the weight is applied downwards, right? Okay? And again, in this problem, we know something about AY, right? He's moving upwards at a constant velocity, which means AY is 0, right? Anytime you're moving at a constant velocity, your velocity is not changing, which means acceleration is 0, right? So that goes away. So that basically means these guys are equal, right? So I'm just going to put a 2 here because we're just adding two equal things. So 2 times, and then the y component is just going to be 200 cosine of 20, right? Minus mg equals 0. Okay? So this is going to be 400 cosine of 20 equals, I'm going to add the mg to the other side, right? G is, of course, 9.8, right? And now I just want to solve for m, right? What is the mass of this person such that if the calf is applying those two forces upwards, right, he is going to lift up at a constant velocity, okay? Well, I just put in my 400 and my cosine 20 into a calculator, divide by my 9.8, which is the gravity here, and my mass is going to have to be 38.3 kilograms. Okay? So just to break down what's happened, we, instead of worrying about just one dimension, we're worrying about two dimensions here, right? We know that these forces are applied both in part to the x and in part to the y, right? And we also know that we have a weight going down, which is in the y direction. We analyzed the sum of the forces in x. We said, okay, there's an x component of this force in this direction, and there's an x component of this force in that direction. They cancel out, right, because it's symmetric, it's the same forces. That's going to happen sometimes. And then I analyzed everything going on here in the y dimension, okay, by adding up the two components of the muscle forces going up, right, and then subtracting the weight on this calf going down, okay? And so I end up solving for the mass that requires me to have a constant speed or zero acceleration going upwards if those forces are applied to the ankle here, okay? All right, so take a moment, look at that, see how we broke this down into two different dimensions, and then feel free to move on to misconception question number 2 over here. So it says, in which situations is it possible that the block is stationary, and in which cases is it possible that it's moving with a constant velocity? Okay, now from the perspective of forces, those are the same exact things, right? Constant velocity and stationary both means A equals 0, all right? So that's kind of a trick. So that implies you should get the same answer for both, okay? But basically the question is, in which of these cases is it possible to balance all the forces, okay? So given what we know about these two equations, right, the forces will only balance if the forces in x can cancel, right, and the forces in y can cancel, okay? So take a moment, maybe pause the video if you need to, and see in which of these cases is it possible for forces in x and y to cancel. Okay. You should be getting an answer of 2 and 4. And here's why. So for 2, right, we have this fellow with a force this way and a force this way, right? There's no forces in y, so there's, that's an equilibrium in y direction, right? But in the x directions, right, this force and this force is possible, it's conceivable that they cancel out because there's, one force going this way and one force going this way. That it is possible for this to be stationary or have a constant velocity because it's an equilibrium, right? In the case of 4, right, we have a box that has something like this, something like this, and something like this, right? Now, this guy is partly pointing in the y direction and partly pointing in the x direction. So we can say that this has a y component here. So if this is f, this would be like fy, and this would be like an fx component, right? Because this guy's pointing in both directions. It's possible that that cancels with that, and it's possible that that cancels with that, so that this guy can also be in equilibrium. Now, let's look at number 1, for example, right? In number 1, you have this situation with a force in this direction and a force in this direction, right? This guy here, this guy has a y component, right? This force is partly pointing in the y direction that's not balanced by anything going down. Do you guys see that? This y component is not balanced by another force pushing downwards here, right? So in this case, there is no way this guy could ever be in equilibrium, because even if there's an x component here that balances out this x component in the positive direction, there will still be a y component here that will surely accelerate this guy upwards, okay? And then I will leave number 3 for you guys to prove to yourself that this guy is not, it's not possible that this could be in equilibrium, okay? For similar reasons as 1. So go ahead, give that a shot, and I will meet you in the next video to discuss Newton's third law.